Welcome! In today's video we are talking about complex square roots. Complex square roots are, as in the real numbers, defined by an equation. If I take an arbitrary complex number z, then any solution of this equation here, w squared equals z, is called a complex square root of this number, or for short, simply root of this number. And famously in the complex numbers, it is now possible to have square roots of negative numbers. Of course, in the real sense, because in the complex numbers there is no order relation. So what are the complex roots or square roots of -1? Well, we have to look at this equation, w squared equals -1, and we already know I and then of course minus I satisfy this equation. So we have found two square roots, namely I and minus I. We are still avoiding this notation, square root of -1, which has to be very carefully defined in order not to lead to contradictions, because here what would be the square root of -1, plus I or minus I? Observe, it is not possible, as mentioned before, to define this as the positive solution, because there are no positive numbers in Z. So see below where we are going to define what this notation means, but we can already state that something like this is now possible, whatever this means exactly. Now, two easy remarks. If I have found one square root of a complex number z, then I have already found another one, because minus w is also a square root, because if I square minus w, this is -1 squared times w squared. This of course is 1, so this is w squared, and by definition this is z. So here, if I have found I as a solution, I already know that minus I also is a solution. That means for any complex number not equal to 0, if I can find one complex root, I also have two, because w and minus w can't be the same number, because they are not 0. On the other hand, one can show any complex number can have at most two square roots. This can either be seen geometrically, as we're about to do shortly, or if we use the fact that a polynomial of second degree in the complex numbers can have at most two roots. The proof is the same as in the real numbers. Then you know, because any complex root of z is a root of this polynomial, there can be at most two roots. And the crucial point will be that in the complex numbers, for any z, this thing here has one, meaning then two different roots if z is not 0. So now for a more challenging example, we are trying to find the square roots of the imaginary unit I. We are doing this in two ways. Way one, or method one, is the hard one. We're using the Cartesian form, try to find the square roots, and then compared to this, the very easy method of using the polar form. And I think doing it both ways makes you appreciate the polar form even more, because this is quite a bit of work. So we write the w, the root, the w also because in German root means Wurzel, written with a w. That's why I chose w here. So w, let w be x plus yi. Important as always, x and y real numbers. And we want to find these x and y such that w squared is I, because then this is by definition a square root of I. So we expand this square using the binomial theorem. This is x squared plus 2xyi plus yi squared. This here is y squared times -1, because I squared is -1. So I pair this with the other real expression, x squared, and then I have plus 2xy I, and I want this to be equal to I, meaning the complex number that can be written as 0 plus 1 times I. So, and now I compare the real and imaginary parts, because two complex numbers are equal if and only if their real and imaginary parts are the same. So x squared minus y squared must be 0, equation 1, and 2xy must be equal to 1, which is equation 2. So from this here I can conclude that x must be plus or minus y, and now this is important because this also must hold. They must have the same sign, because if x would be minus y, they would be, one of them would be negative, so the product couldn't be plus 1. So because of this equation we can lose the minus sign. So here it is again, because of equation 2, xy must be positive, otherwise this couldn't be plus 1, so x must be y, they must have the same sign. So plugging this into equation 2, we obtain 2xy equals 2x times x, so 2x squared. This must be 1, so x squared is 1 over 2, 1/2. We take the root, the real, very important, this is the real root, the root in the real numbers. So we have plus minus square root of 1/2, which is the same as 1 over square root 2, or making the denominator rational yields plus minus square root 2 over 2. And then of course this is y. So we have found square roots, two square roots of the imaginary unit I, namely square root 2 over 2 times 1 plus I. Simply plugging this into here and pulling out this factor. You should check for yourself that indeed, if I square both of these numbers, I end up with I. And now, of course, you don't really want to do this whole calculation whenever you're looking for a complex root. So now the polar form comes to help, and this is a big advantage to use the polar form. Actually, this calculation can be done for any complex number a plus bi, giving you a rather huge formula that we are going to discuss in one or two of the next. But that isn't actually as bad as it looks, and we are going to discuss it in depth in one of the next videos. Okay, here we go. Method 2, which is much easier. We are using the polar form. So we are looking for complex numbers of this form that satisfy w squared is equal to I. Now to square this number, I square the length, the absolute value, r squared, and I take e to the phi I squared. And as for the real exponential function, the complex exponential function satisfies the same laws, so I can rewrite this pulling the 2 inside of the exponent. So this here is 2 phi I. And I want this to be I. And I is 1 times e to the pi over 2 times I. And now just by looking at it, I can at least see one solution, because r squared must be 1. So r, of course, is 1. R can't be negative. And 2 phi must be equal to pi over 2. That's very easy to solve for phi, right? So one solution is given by r is equal to 1. Minus 1 is out of the question because r must be positive. And 2 phi is that, so phi is pi over 4. So we already have our first solution, our first complex square root of I. And if you compare this, this is ridiculously easy in comparison. Using Euler's identity, of course, you can show that this yields exactly one of these solutions, because this here is cosine of pi over 4, which is square root of 2 divided by 2, plus I times the sine, which has the same value. And if you pull the square root of 2 over 2 out, you end up with this solution here. And of course, as remarked before, if I have found one solution, then its negative is automatically a second solution. So we have found two square roots. You can again check or see this is the same as this here with a minus sign. And as remarked before, there can't be more than two solutions. So we have found the two square roots of I. Now here, this can also be interpreted geometrically, because minus 1, by the famous equation, can be written as e to the pi I. Minus 1 is the arrow that points in this direction, so its angle with the real axis is pi. So I write this minus 1 here as this exponential term, and now I use the fundamental property of the complex exponential function, which tells me that I can add the exponents, so I end up with pi over 4 plus pi. I switched around here the two summands. And now this is interesting, because I take this arrow, e to the pi over 4 times I, and what do? I rotate it by 180 degrees, or by pi. And now what happens to this rotation when I square the arrow? Then this gives me 2 pi, and 2 pi I cannot notice, because this is one whole rotation of the arrow. That's the geometric reason behind this minus here. We showed it algebraically that minus 1 squared vanishes, but geometrically it's even better, because this minus 1 corresponds to a rotation by pi, which I cannot see anymore when these arrows are squared. So if I square these two arrows, I end up with the arrow for I pointing straight upwards. Okay, now by generalizing this idea, we end up with proposition 9.8. Every complex number, here written in polar form, r times e to the phi I, which is not a zero, has exactly two complex square roots. The first one is given by taking the square root, the real square root of r, and dividing the argument or angle by 2. That's it. And the other one, of course, is the negative of this one here, which can be geometrically written as adding pi to phi over 2. And we don't actually need to prove that, because it should be obvious that this here is a square root, because if you square it, you end up with this number. Same for this here. And we already said that there can't be more than two square roots. Using this polynomial argument here, if you don't like that, you actually have to write any solution in the form s times e to the theta I, square it, do this calculation, and then you need to know about the zeros of the cosine and sine function. You split this up here using Euler's theorem, and then you need a fact about the zeros of the sine and cosine functions that we can prove in this context. So either way, it should be clear how you arrive at this result. You take the square root of r and divide the angle by 2 and take the negative. I think that's enough at this point. And now to conclude, we still haven't defined this symbol, because so far we have an ambiguity that we cannot resolve as in the real numbers by saying, well, we take the positive solution. Remember, there are no positive complex numbers, so we can't just say, well, this here is not the square root, but we define that the square root, this symbol, the square root of any complex number z is the solution of this equation whose argument lies between 0, 0 included, and pi, pi not included. So geometrically, we're taking the upper half plane, but we're taking out the negative real axis, because here we would have the ambiguity that either -1 and 1 squared give you 1. So the square root of 1 would be ambiguous, which of course we do not want. So for short, this symbol means you take the solution of this equation that lies in this slitted upper half plane. I call it h minus because I take out the negative real axis. So for example, the square root of -1 is here, e to the pi over 2i, which of course is I, and not this solution here, e to the 3 pi over 2i, which would be this dotted arrow here, minus I. Yeah, we take this arrow that lies in the upper slitted half plane, and the same goes for square root of I. It is this solution and not this one here, the dotted one. Here, the dotted blue one. So we take this solution. Here again it becomes apparent what happens geometrically, because if you multiply this red arrow with itself, we know that the angles have to be added. So adding a 90-degree angle, I end up with 180 degrees, giving me -1. And the same for the blue arrow, adding the 45-degree angle with itself, I end up with 90 degrees. Because the length already is 1, I end up with length 1, so with I. And now this is a very special moment, because remember when we started talking about complex numbers, we said that we cannot begin using this as a definition. This would be completely senseless. We used Hamilton's approach, did everything by the book, nothing mysterious at all. And now finally we actually know we can define in a proper way what the square root of -1 actually is. Okay, so much for now. There are going to be 1 or 2 more videos about complex square roots. I hope you enjoyed the explanations. Thanks for watching, and see you soon on this channel if you like.